Good morning. Okay, it's actually not really morning. Well, it's almost morning. Kind of sadly. Uh, I live in this yellow area here, and it's actually pretty close to morning. It's morning in the red area. Uh, I tried to do this video once already today. I tried to do it when it actually was morning here, and it didn't work. I had some technical difficulties. And so I was actually listening to a hockey game that was taking place in this green shaded area over here, where it's 2 hours earlier. And that game's finally ended, so hey, I can come back and talk. So I got a message on Sunday. It's Tuesday night as I record this. And I got a message on Sunday from a friend of mine that gave me a conditional probability problem. And I looked at it for about a minute and said, I know the answer. And I gave the answer. She said, yeah, that's the answer I got. But a lot of people from where I found this question are getting this wrong. And I talked to her about another problem in conditional probability and said, you've actually made me want to make a little mini lecture. So that's what I'm going to do. I'm going to record this little lecture here. So this is my conditional probability mini lecture. It should run about 15 minutes. This morning it ran 14 minutes and 53 seconds. So I've got a question that involves coin flipping. There's some mistakes in looking at that problem. I want to look at what the right answer is and some of the incorrect results that come from making mistakes. You probably hear I really should move the microphone so that you can hear me better. Hi. This isn't my setup. This is my spouse's setup, who does Twitch streaming, and this is my dog. Yes, here she is. Hi. This is my dog. And so often when my spouse will do Twitch streaming, my dog will show up because she's hoping that she gets a treat from the streamers. And sometimes she doesn't. Earlier today, she actually got one. You might see the bag of treats over here. So that might happen at some point. We'll see. Anyway, after I talk about the coin flipping, I got a similar problem I want to talk about. That gives us some interesting assumptions and gives us information that we don't think is going to be relevant and a little bit of a surprising answers. So let me start off with the original question that my friend sent me on Tuesday. So here it is. You flip 3 fair coins. Given that one of them is heads, what's the probability that you got at least 2 heads? All right, so I want to talk about what this means. In case you're not terribly familiar with probability, we got some terminology here. Experiment, outcome, sample space, event space. These are important terms in probability. An experiment is some process with an unknown result. I don't know what's going to happen. Okay, it's like the hockey game I just listened to. At the start of the game, I don't know who's going to win. I hope the team I want to win wins. But, who knows what's going to happen. Turned out they did win, 6-2. I'm happy about that. But, so an outcome is a possible result of an experiment. There's an outcome. My team winning. That was a possible outcome. Another outcome would be my team losing in regulation. Another outcome would be my team losing in overtime or shootout. That's actually a different result, the way the hockey standings work. So, outcome is a possible result of an experiment. The sample space is all possible outcomes for an experiment. Anything that could possibly happen is in that set. And then an event is a subset of the sample space. So, if we're talking about flipping 3 coins, we're going to have a sample space that's a set of the results that we could get from flipping 3 coins. The event that we're talking about is getting at least 2 heads. So we're going to be looking for the outcomes out of this set of all possible outcomes that give us at least 2 heads. So tossing a coin is an example of an experiment has 2 possible outcomes, heads or tails. So I've got a picture of a coin here, heads and tails. My birth year is 1976, so I featured 1976 coins in this presentation because I could. Saying that an experiment is fair means all its outcomes are equally likely. So for a fair coin, we've got these two possible outcomes, heads and tails, and it means they're equally likely. So if I toss a coin 50,000 times, I expect about 25,000 of them to be heads and about 25,000 of them to be tails. Equally likely, I should have close to the same number of each one. All right. So what are the possible outcomes if we toss 3 coins? We're interested in the number of heads that show up. We have 0 heads, 1 head, 2 heads, or 3 heads. So 2 of these outcomes are at least 2 heads, except we've got a problem. If we're talking about probability, the problem with this as our possible outcomes is they're not equally likely. I mean, there's nothing wrong with saying the possible outcomes are 0 heads, 1 heads, 2 heads, and 3 heads, and saying that that's our sample space. But the problem with that is that they're not equally likely. And a lot of times in probability, students make an assumption that the outcomes are equally likely, even when that really doesn't make sense. Just as an example, if I go to take an exam, there are 2 possible outcomes for the exam. I pass the exam or I fail the exam. That's a fine way of looking at that problem. Are those outcomes equally likely? Well, gee, I hope not. If I go down to the foreign language department and I sit in a German class and I take a German exam, probability that I'm going to fail it is really high because I don't speak German, I don't read German, I don't know basically anything about German. Yeah, that's not me. What's that? French I could deal with. English, okay. Anything beyond that? Nah, not really. On the other hand, if I go down the hall to another math classroom and I take a Calculus 1 exam, I've taught Calculus 1 I don't know how many times. I'm pretty confident in my abilities in Calculus 1. So I'm pretty sure I would pass the exam in Calculus 1. As soon as I look at that and say, there's something I could do to affect it, and this is what students come up with. They're like, well, I could study for an exam, or I could, not go out partying the night before the exam. If there's something you can do to affect the outcome, then they're not equally likely. And that's not what we want here. We don't want a situation where the outcomes are not equally likely. And just to demonstrate that the outcomes here are not equally likely, I want to give a little example here. So I built a simulator for 3 coins. And let me move my face out of here so you can see the numbers. Just built a simulator with a spreadsheet. 0 heads, 1 heads, 2 heads, and 3 heads out of 1,024 tosses. And we find that, hey, 1 head happens a lot more often than 0 heads, almost 4 times as much. 3 heads happens more often than 0 heads. Now, different runs of this simulator are going to give us different numbers. Here's actually the spreadsheet that I had for the simulator. And if I press a key here, I'm going to change the numbers. But what you should notice about these numbers, even though 0 heads might go up to 140 or might go down, there was 103 there, it's usually staying somewhere above 100. There's 153 I saw, somewhere below 160. They're all below 200. Same thing with 3 heads. 3 heads and 0 heads seem to go, right here they're exactly the same, both 125. 3 heads and 0 heads look like they're close to the same value. 1 heads and 2 heads are much higher. In fact, 1 heads and 2 heads, if you look at the numbers, seem to be in the high 300s, whereas 0 heads and 3 heads seem to be in the low 100s. So clearly what we can get from this information, even if we don't know exactly what the numbers are, is we know that they're not equally likely. No, definitely not equally likely here. Okay, so back to our argument here. What we want is equally likely outcomes. So can we fix our model? Well, here's a couple of ways we could do that. 3 different coins. Say I've got a dollar coin, a $50 coin, and a $quarter coin. This outcome on the left here has President Kennedy's face and the Liberty Bell and the drummer boy. Over here we got President Eisenhower's face, Independence Hall, and the drummer boy. Both of these are 1 heads, but they look different on the page. Also, 1 coin flipped 3 times in order. Here we have General Washington in the middle. Here we have General Washington in the left. They look different. Now, it turns out that if this is our approach, if this is our model, we have equally likely outcomes. But obviously, the numbers are different. So what happens here, again, get rid of my face, because if we want equally likely outcomes when tossing 3 coins, this is one way we can do it. So this is our orderings here. And we have 0 heads. We have 1 head in the first, second, and third position. We have 2 heads with the tail in the first, second, and third position. Or we have 3 heads. Now that's 8 outcomes. And in each of these 8 outcomes, we have equal numbers of heads and tails in each position. So if I just look at the far left, 1, 2, 3, 4, 3 of those were tails. 1, 2, 3, 4, 3 of those were heads. So we have 4 heads and 4 tails. Same in the second column, same in the third column. Now, I want to emphasize here we have not changed the original problem. All we've done is made modeling the problem easier because we now have equally likely outcomes, which is much easier to model. Okay, so now what? Well, there's an interesting piece to this. We had this given that one of them is heads. What does that mean? So the way I explain this when I'm talking about this in the classroom is imagine you're sitting in the classroom and you get a problem that says, all right, you're going to flip 3 coins. And then you hear somebody out in the hall yelling, hey, I saw one of the coins. It was heads. Okay. That's information. We know something we didn't know before whoever was out in the hall yelling at us gave us this information. That's what conditional probability is about. Given that one of them is heads means exactly that. Somebody told you something. But now we have to be careful about what exactly did they tell you. Now all they told you here is that one of them is heads. All we really know from that is that we don't have this situation. We don't have all 3 tails. We had to have a head somewhere. So that means we throw out one of those 8 outcomes from our sample space. We restrict the sample space. We make it smaller. Now the event space is actually over here on the right. Because again, we're looking for 2 heads at least. So 2 heads, 2 heads, 2 heads. Last one is 3 heads. So the 4 over on the right there, over here, that's our event space. The 7 we see on the entire screen here is our sample space. There's our answer. 4/7. That's the probability of having at least 2 heads if we know we have at least 1. Okay, so how can we mess this problem up? Common mistakes. So one common mistake for this problem, as I mentioned earlier, is assuming equally likely when we don't actually have that. So one way to mess up this problem is to look at it and say, okay, well, let's suppose I've got 4 possible outcomes, 0, 1, 2, or 3. Well, 2 of those are the outcomes I want. Out of 3 that are possible, because we really still can't have that 0, so it must be 2 out of 3. And that would work if we had equally likely outcomes. We don't. That's a problem. But if we had equally likely outcomes, that would work. All right. Another common mistake would be forgetting about that voice from the hallway that's telling us, hey, we know you don't have 0 heads. If I make that mistake, I've now got 4 out of 8, or 1/2. Incidentally, if I combine this mistake with the previous mistake, that is, I don't gray these out, well, again, I got 2 out of 4, which is 1/2. Now, my friend actually told me that most of the people who were responding to this question from the place where she found it were giving the answer of 1/2. So this is the mistake they were making. They don't know how to deal with that voice from the hallway that's saying, hey, you've got at least 1 head. They were ignoring that. Well, that's wrong. You can't forget this information. But if you do, that's what happens. There's one other mistake that I see a lot with this, and it's on this what does this mean? So again, all this means is that the person out in the hall saw one of the coins. We don't know which one. And said that it was heads. But what if we asked which one and got an answer? If we get the answer to this question, we have a different problem. If we ask which one, and we have our 3 different coins, the dollar, the half dollar, and the quarter, or if we ask which one and we toss them in order, first, second, third, then the person can say, all right, I know which one is ahead. That's going to make a difference. Here's I saw the first coin, it was heads. Well, now here's our sample space. We only have these 4. And the bottom 3 have at least 2 heads. So now the answer is 3/4. Here's the same thing with the 3 coins. I saw the dollar. It was heads. General Eisenhower was staring back at me. Okay, all right. So what does that leave? Well, we could have 2 tails from the other 2, or 2 heads from the other 2, or a head and a tail, or a head and a tail. This problem, and actually so did the last one, has become, you flip 2 coins, what's the probability that you get at least 1 heads? Because now we've just removed 1 coin, whether it's the dollar coin, whether it's the first coin. We've gotten rid of 1 coin. You flip 2 coins, what's the probability you got at least 1 heads? All right. So that's our coin flipping. So here's the summary. Or if I can put the mouse in the right place. Here's the summary. Correct answer is 4/7. If we know nothing about any of the coins, the answer would be 1/2. If we don't have that given that one of them is heads, the answer would be 1/2. The more we know about heads, the higher the probability would be. Up to a limit of 3/4. If we know a specific coin was heads, we have a limit of 3/4. Notice 4/7 is somewhere in between 1/2 and 3/4. So we start with 1/2 with that no given information, and as soon as that person in the hall starts yelling at us, the probability is going to go up. As long as the person in the hall is telling us we know about heads. If the person in the hall was telling us we know about tails, the probability would be going down rather than up. But here, because we're looking for heads, the person in the hall is telling us about heads, the probability is going up from 1/2. And the highest it would get would be 3/4 if that person told us, hey, I saw a specific coin that I know is a head. All right, so that's pretty straightforward. I want to look now at a different problem, similar idea. It's a problem that I got from a colleague of mine. Actually, I was standing in the hall talking with another instructor, and this professor came out of his office and gave us this problem. We both looked at him and said, that doesn't make any sense. Why are you asking us this? That sounds like a completely useless piece of information. It must mean something that we're not expecting because you're asking about it. And it turned out, and we both went and independently both went back to our offices and worked on the problem and came back with, I don't believe what I just got, but yeah. So this is a situation where that condition is going to sound weird, but actually is going to turn out to be meaningful. Kind of like what we had last time. The more information we get, the more the probability changes. So here's this new problem. And wrong one. There we go. Here's this new problem. And I got this from, let me talk about the problem first. The problem is going to involve somebody having children. And for the purpose of this problem, I'm going to make the following two not entirely correct assumptions. Assumption number one is that the only two possible outcomes of a child being born are boy and girl, and they are equally likely. Now, that's not exactly true. If you look at census data, you find boys and girls aren't exactly equal. One is a little bit more common than the other one. I honestly am not sure which, but I know that they're not entirely the same. Also, we're going to assume that births are uniformly distributed through time. Basically, there's no more common time or less common time for somebody to be born. And for the purposes of this question, what's going to matter is that each day of the week that a person could be born on is equally likely. Now, that's not entirely true. And the main reason that's not entirely true is because we have induced births, we have surgical births, we have things that happen on kind of a non-emergency basis that are more likely to happen during the day on a weekday than at, say, 3 a.m. on a Sunday. But we're going to make those assumptions because equally likely is nice. And so we want boy and girl to be the two outcomes and have them be equally likely. And we want the 7 days of the week to be 7 outcomes, and we want them to be equally likely. So here's the problem. And I've named, wrong direction. So I've named this problem after Leonard, because Leonard is the name of my colleague who gave it to me. Said Leonard has 2 children. Given one of them is a boy, what's the probability that they're both boys? This problem is very straightforward. It's similar to the coin tossing problem. In fact, it's exactly the same as a coin tossing problem that says Leonard tosses 2 coins. Given that one of them is heads, what's the probability that they are both heads? It's the same problem because our model for children says we have 2 outcomes, boy and girl, and they're equally likely. Toss a coin, fair coin, means equally likely for heads and tails. All right, so here's our 4 possible outcomes. This is the first child across the top. It's either a boy or a girl. This is the second child down the left. It's either a boy or a girl. And here are the 4 possible outcomes. Now, again, like with the coins, I've imposed something here. I've put an order on the children. I've got across the top, boy, girl. for the first child, and down here, boy, girl, and I've said that's the second child. The only reason I do that is because, well, I'm going to have 3 possible outcomes, right? Boy, 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 girl, or girl, girl. But looking at this, it becomes obvious that boy, girl is actually more common. 2 out of the 4 give me boy, girl. Only 1 boy, boy, only 1 girl, girl. Now, the given that one of them is a boy only gets rid of this outcome over here. It's gone. I can't have that. I cannot have girl, girl. It's the only thing I know. It's the only restriction on the sample space. So I've got 1, 2, 3 other options. Boy. Boy, boy is one of those options. Well, there it is. 1/3. Okay. Sound good? All right, what if the person who's giving us this information has something more specific? So I'm gonna call the person giving us the information Jay, because that's Leonard's office mate's name. So suppose Jay comes in and says, "Oh yeah. You know Leonard has 2 kids, right? Well, I met one of them and it's a boy." That's what we've had so far. But suppose we change the problem and now Jay says, "Oh yeah. I met his older child, and his older child's a boy." This is much more specific information. This is like the dollar coin was a head. More specific information. So now, it's actually this whole column that I know is wrong. The older one is a boy, so I don't have those outcomes. Well, that means I only have 2 outcomes, and one of them is both boys. So now my answer is 1/2. This question, because Jay gave us all of the information about the older child, well, all the information we care about, we're only looking at gender here. We know the older one's a boy. No problem. The problem has been reduced to, what is the probability the younger child is a boy? Again, only 2 possible outcomes for gender. According to the assumptions of our problem, they are equally likely. 1/2. That's it. That's what the problem has become. All right. Here's the curveball. So Leonard walks into the hall and walks up to the 2 of us talking outside the faculty office next door to his. And he says, "Hey, I got this problem for you. Okay, suppose somebody has 2 children. You're given that one is a boy. What's the probability they're both boys?" And we're sitting here, yeah, 1/3. That's easy. He said, "Yeah, okay. Now, what if we know one of them is a boy born on a Tuesday?" So this is Jay coming out and saying, "Hey, I met one of them. It's a boy. He was born on a Tuesday." Now, I want to make clear, I am not saying here that Jay says, "Hey, I met one of them. His birthday's today." Now, granted, if we look at it's not going to give me my time now. It's actually no longer Tuesday here for some bizarre reason. This fancy thing that I've been working on is not giving me what it's supposed to be giving me. But it is after midnight now. It is Wednesday in this time zone. And I'm not saying that, oh, hey, today's his birthday. Because that would actually be a lot more specific. A lot more specific. Again, we're assuming that time is continuous and births are evenly distributed. I'd now have like a 1 out of 365 or 1 out of 365 and a quarter, roughly, of narrowing down this kid's birthday. Now I only have a 1 in 7. But that 1 in 7 is still going to give me some very interesting information. So let's take a look at it again. So this is more specific than the first one. Because the first one was just, we know one of them is a boy. Now we're being told, hey, we know one of them is a boy born on a Tuesday. So here's the grid. A lot more possible outcomes. 196 possible outcomes, actually. 2 genders, 7 days in a week. That's 2 times 7 is 14. So there are 14 possibilities going across. I got 14 columns, 14 possibilities over here. I got 14 rows. 14 times 14 is 196. But we can eliminate a whole lot of these. Specifically, I only care about this column and I only care about this row. Because everything else does not have a boy born on a Tuesday. So here we go. I've grayed out everything else. So what do we got? Well, I don't care how you count this, you're going to come up with 27. 14 in this row, 14 in this column, 14 plus 14 is 28. Minus, you've double counted this one, is 27. How many have I lit up in blue? 7 in this row, 7 in this column, 1 double counted. 7 plus 7 minus 1, 13. So I got 13 out of 27. That's pretty close to 1/2. 14 out of 28 would be exactly 1/2. We did that, subtract 1 from each one. Gives us pretty close to 1/2. And actually, it turns out that however many categories we have to pick from, you get 2 times that minus 1 over 4 times that minus 1. So when we only had 1, going back to this question, it was 2 times 1 minus 1, that's 1, over 2 times 2 minus 1, that's 3. Here, it's 2 times 7 minus 1 over 4 times 7 minus 1. If we had the, hey, I went and saw one of Leonard's kids yesterday, since it's now Wednesday. I went and saw one of Leonard's kids yesterday. It was his birthday. Okay, now we wind up with 2 times 365 minus 1, or 365 and a quarter. I'm fudging the fact that sometimes people are born on February 29th. Over 4 times 365 minus 1. Well, that's what? 729 over 1459? That's really close to 1/2. So the more information we know about the known boy, we get closer to 1/2. Now, once again, if I know the older boy born on a Tuesday, same old deal. I get 7 out of 14. I get 1/2. So just like if we didn't know about the Tuesday, if we know the older boy, that trumps everything. Because now I've reduced it to what is the probability the younger child is a boy. So summary about this one. The correct answer to, given that one of them is a boy, what's the probability that they are both boys, is 1/3. If we know the boy we know about was born on a Tuesday, the answer is now 13/27. Really? Yeah. Even though that piece of information doesn't seem like it's relevant, the more we know about the boy we know, the higher the probability becomes that they're both boys, to a limit of 1/2. If all we knew was the boy that we know about was born in the morning, was born before noon, well, that would be 2 possibilities. So we'd have 2 times 2 minus 1 over 4 times 2 minus 1. We'd have 3/7. Well, that's more than 1/3, less than 1/2. Again, we've got a continuum here from 1/3 to 1/2. And the more we know, the closer we're going to get to 1/2. Just like with the coins. With the coins, it was the more we know about the one coin that we know is ahead, the closer the probability gets to, what was it, 3/4? Yeah. The closer the probability gets to 3/4. Starting from 1/2, heading up. So all we knew is one coin is ahead. That's 4/7. Here, starting from 1/3, we approach 1/2. The more we know, the closer the probability gets to 1/2. So that's my little lecture here. Wow. Okay, it says that I'm at about 36 minutes, which is either twice as long as this took me this morning, or more likely, I was really having a lot of technical difficulties this morning, so much so that the recording software I was using gave me the wrong quoted time. So anyway, it's been 36 minutes. I should probably stop. But I wanted to do a little talking about conditional probability. And honestly, this was fun. Probability is something that I like. It's something that I enjoy. And so it was fun sitting down and making out this lesson and recording a lecture about it. Something I haven't been able to do for a while. So I enjoyed this, and I hope you enjoyed watching it. And well, that's it. Bye.